This work example uses StarDrop Surflex eSim3D module to assess a small library of compounds for their similarity to known HSP90 ligands. The library, created by a de novo design process, contains compounds with a beta-resorcylic acid core. The objective in this example is to use the Surflex eSim3D module to develop an understanding of the 3D structure-activity relationships and then use multi-parameter optimization to assess the similarity score together with the ADME and physicochemical properties of the library. In StarDrop, open the project file hsp90.sdproj by selecting Open from the File menu. This opens a dataset of 9 virtual HSP90 inhibitors. The compounds are based around a known HSP90 inhibitor on a lespib and share a beta-resorcylic acid core. To investigate how similar these compounds are in terms of their shape, electrostatic potential, and hydrogen bonding potential to onalespib, we will do a similarity analysis. Select all compounds of the HSP19 virtual library dataset by clicking in the top left corner of the dataset. Click the Go button and select Calculate Alignment Similarity. This will prompt you to choose an alignment reference molecule to which to align your compounds. We will use the HSP90 inhibitor onalespib as the reference, and we will obtain the bioactive conformation of onalespib from a co-crystal structure. Click the Download button to obtain the ligand from a PDB reference. Enter the PDB code 2XJX and click OK. A dialog box appears suggesting an alternative protonation state for the nitrogen on the piperazine ring. Click OK to accept the protonation. In the name text box, enter align_crystal. There are further options such as the ability to add torsional and positional constraints if you select the advanced options. However, we will use the defaults. Click Next. This page gives the option to define the parameter scheme of the alignment similarity analysis. The parameter schemes vary in terms of speed and accuracy. Click Finish to run the alignment with the default option. Once the alignment finishes, the calculated similarity value is added to our dataset in the column called align_crystal. A number is added to the structure column, which is the number of alignments it has generated. Select compound 1 to show it in the 3D viewer, aligned to onalespib. We can view the aligned conformations by clicking the number next to the structure. The best scoring conformation is the primary pose, which is denoted by a star symbol. You can change the primary pose by selecting the conformation and then clicking the star button. Right-click on the align_crystal column to bring up the menu and choose Sort, then Descending to bring the compounds with the highest similarity values to the top. We can see that the most similar compound to the co-crystallized ligand is compound 7. Select compound 7 in row 1 to see the alignment in the 3D viewer. There is good alignment with the beta-resorcylic acid core and isoindolin regions of our reference compound. However, compound 7 is much smaller and doesn't have a portion that aligns with the piperazine ring. Therefore, despite its alignment, the potency might be much lower. Select the Display Options button to bring up the Surflex eSim3D display options. Select the Show Surface option and explore the similarity and dissimilarity surface maps to see which regions of compound 7 align well. Finally, select the Difference option and check the box next to the hydrogen bond donors. We can see there is a difference highlighted around the distal piperazine. Compound 9 is in row 3 and has the opportunity to substitute the amide NH to reach the space occupied by the piperazine. A direct methylene link to a piperazine would not be stable in this compound. Therefore, we can instead design a piperidine or pyrrolidine. To save time, we have included suggested ideas based on compound 9 in the fourth dataset of this project. Click Close to close the display options. Then select the Suggested Ideas dataset and select all 3 compounds by clicking in the top left corner of the dataset. Go to the Edit menu and select Copy. Then go back to the HSP90 virtual library dataset, go to the Edit menu and select Paste. Finally, select the 3 new compounds. Then click the Go button and select Calculate Alignment Similarity. The reference we chose in our previous analysis is saved, and we can simply click Finish to align these new compounds to the reference compound. Despite the obvious 2D overlay, these derivatives don't score as well because they disturb the resorcylic acid alignment. Alignment score isn't everything, and these derivatives may be superior in other properties. Therefore, we'll use StarDrop's probabilistic scoring approach to multiparameter optimization to assess each compound's properties against the overall profile required by the project. We can then use this score to track our progress as we attempt to design compounds with an improved balance of properties. Select the Scoring tab and run the scoring profile called HSP90 Scoring Profile with Alignment Similarity by clicking the Go button. A message will appear stating that the align _ crystal column doesn't have an uncertainty associated with the data. You can click OK to continue. The score is in the range of 0 to 1 and represents the likelihood of success of each compound against the overall profile or property requirements, taking into account not only the property values but also the uncertainty in each prediction or measurement. The histogram shows the impact of each individual property on the overall score. The colors correspond to the key in the scoring profile. By hovering the cursor over the histogram, we can see that there is a lower bar for the align _ crystal similarity score for 2 of the new ideas. Just as designing against one property could lead to biased and missed opportunities, comparing the alignment similarity to only one ligand might induce bias. There are several ligands which bind to HSP90, and 5 are included in the HSP90 ligands tab. We shall use all of these ligands to generate a binding hypothesis to gain a better understanding of the potential shape and interactions of an ideal ligand. Select the second dataset of the project called HSP90 ligands. This dataset shows onalespib and 4 other compounds which have also had their HSP90 bound conformation determined. These compounds all contain the beta resorcylic acid core. Select all compounds of this dataset by clicking in the top left corner of the dataset. Then go back to the 3D area and click the Go button to select Generate Binding Hypothesis. The parameter scheme specifies how intensive a search to conduct for binding hypothesis is. Choosing an intensive calculation will lead to more accurate results, but will take longer to compute. You can set additional configuration options by selecting Advanced, but in this case, we'll use the default setting. Click Finish to start the generation of binding hypothesis. This will take a few minutes to complete. If you would not like to wait, you can view the results in the third dataset of the project called HSP90 ligands pre-calculated by clicking the View Results button under the 3D viewer. There are 10 binding hypotheses generated, and the probability of each of these hypotheses being accurate is shown. Select the Display Options button to bring up the Surflex eSim3D display options and explore the similarity and dissimilarity between these compounds. We can see good alignment around the beta resorcylic acid region. Regions where there is similarity in the shape or potential interactions between the ligands indicate likely steric constraints or conserved interactions. Areas of steric dissimilarity indicate regions where there is more freedom within the binding site. We now have a better reference for the virtual compound alignment, as it is made up of several examples of HSP90 ligands. We will now compare our virtual compounds to the top binding hypothesis. Click on the cross at the top right of the binding hypothesis results to close them. Go back to the first dataset, HSP90 virtual library, then select all compounds by clicking in the top left of the dataset. Finally, click the Go button and select Calculate Alignment Similarity. Select Define a new alignment reference and click Next. Click the View Results button to select from the binding hypothesis for a reference to align against. Then choose the first binding hypothesis and click OK. Give the alignment the name align_multi and then click Finish in the main dialog box. The calculated similarity is shown in a new column, this time called align_multi. Right-click on this column to bring up the menu and choose Sort, then Descending, to bring the compounds with the highest similarity values to the top. The ordering of the compounds have changed, and the top compounds are now the new ideas. We can see that the similarity score has increased considerably, showing that we are aligning well with the target containing multiple HSP90 ligands. Simultaneously considering different ligands enables us to consider a range of conformation and interactions that could be accommodated by the target binding site. Click on the compound in row 1 to show it in the 3D viewer. Then click on the number of conformation next to the structure to display the drop-down menu showing the available alignments. Select the 4 conformation. The new compounds are likely to have improved potency over the original compounds due to their similarity to known HSP90 ligands. However, potency is not the only factor to consider when optimizing compounds, so we will again use a scoring profile to look at the balance of properties. Change to the scoring area and select the scoring profile called HSP90 Scoring Profile with Multiple Alignment Similarity in the list of available scoring profiles. Then run it by clicking the Go button. We can see that the scores for some compounds have changed considerably due to the better alignment with multi-legal binding hypothesis. We can compare these two multi-parameter scores in the visualization area. Change to the visualization area and select the first scoring profile column by clicking on the column header. Hold down the Control key if you're using Windows or the Command key if you're using a Mac and select the second scoring profile column. We can see that the suggested ideas compounds now score much better than with a single co-crystallized ligand of HSP90. We can draw around data points that differ considerably between the two scores. The alignment scores for compound 3, compound 5 and the 3 new designs improved, translating to better multiparameter scores. This example illustrated how we can use Surflex eSim3D to compare virtual compounds against known inhibitors of HSP90 and use the alignments to design new compounds. StarDrop contains many more features for selecting and designing compounds, and further work examples are available from the tutorial section of the Optibrium community.